So here I'll discuss about the gradient of a function. The gradient is a differential operator in space domain. So I can define the gradient of a function as, see, the operator gradient of function. Say we have a scalar function phi. So the grad of phi is given by the operator. This is an operator. All right. This is an operator in a space domain. Okay, I should rub this. This is an operator in space domain. I have written I over here. So plus k phi. This is an operator in space domain, and this phi is a function. So this is a gradient operator. This is called del operator. Also call it del. It is denoted by this kind of inverted triangle. So this is del phi, gradient of phi. I'll discuss about, we introduced this function, we introduced this operator in the previous lecture that was on directional derivative, right? So we have certain properties of gradients. Let's discuss this. The first property is, we discussed in last lecture. First property was the directional derivative of scalar function phi at a point p x y z in the direction of unit vector a is given by del phi dot a. We studied in quite detail about this in the previous lecture, right? So directional derivative of any function phi at any point p in the direction which is defined by unit vector a is given by del phi dot a. So del phi helps you evaluate the directional derivative. Now I'll move on to the next property, that is, I'll rub this over here, right? So I'll go on to next property before I'll rub it. The second point is, I'll write it, if n, this is another property, if n be unit vector normal to the level surface fxyz equal to c at any point p xyz, and n with the distance of a point p from some fixed point a in the direction of n such that dn represents an element of normal at point p in the direction of n, then grad f is df by dn n, right? So we have to prove over here that the gradient of f lies in the direction normal to the level surface. Gradient of f lies in direction normal to the level surface. Can you tell me the directional derivative? See, the directional derivative is given by del f dot a. Directional derivative in any direction is given by del f dot a. Suppose I have a level surface like this. Suppose I have a level surface like this. And if I ask you if a is tangential, if a lies tangential to the level surface, if suppose a lies tangential to the level surface, can you tell me what is the directional derivative in the direction tangent to the level surface? What does level surface denotes? Level surface denotes a function f equal to constant. So if I am moving tangential to the level surface, which I am moving along the level surface, if I am moving along the level surface, do I find the change in the function f? No, because level surface denotes set of all those points where f is constant. So it means I can say that if I am moving on a curve which lies on the level surface, I don't find the change in f. Any curve on the level surface, if I am at some point on the level surface, if I draw a curve on the level surface and I am over here, then I am moving along the curve. Then if I draw if I ask you, if I am moving on this curve and I ask you what is the unit vector in this direction, unit vector will obviously be tangent to this level surface. So I can say in any direction. See, moving on a curve means moving along the direction of motion is defined by the tangent to that curve. So if I have any direction, if a is a unit tangent vector on the level surface, means I am moving on the level surface. So if I am moving on the level surface, the directional derivative will obviously become 0, where a is a tangent, is a unit vector tangent to the level surface. If A is a unit vector tangent to the level surface, the directional derivative will be 0, because tangent vector direction, if I am moving on the, means if A is a unit tangent vector, it means I am moving on the level surface. On the level surface you don't have F varying, so your dF by ds is 0. In fact, dF by ds is 0. F is not changing at all when you are moving on the level surface. So at any point of time, if I ask you what is the unit vector in the direction of motion, I will say that is a tangent vector. So if A is unit tangent vector, your directional derivative d del f dot A will be 0, since F is not varying on the level surface. So where this will be the case when A is a unit vector tangent to the level surface. Means what? It means del f is perpendicular to any unit vector tangent to the level surface. Any unit vector tangent to the level surface. It means del f is lies in the direction normal to the level surface. Since it is perpendicular to the unit tangent vector, so I can say del f lies in the direction normal to the level surface. It lies in direction normal to the level surface. So I can write this as del f equals to something like df by, if I am moving in normal direction, it's nothing but df by t, and del f lies in direction of normal. Del f lies in direction normal to the level surface, right? So this is the case. This del f is, if you are moving along direction normal to the level surface, if I am moving along direction normal to the level surface, in that case your df by dn will be given by del f dot n, and since del f itself lies in direction normal, this is nothing but magnitude of del f. So I can write del f as df by dn magnitude into the unit normal vector. So del f lies in the direction normal, so I can write like this. This is yet another property. You try to understand, when I am moving along the level surface, or you are moving in the direction tangent to the level surface, then your directional derivative is 0, because the function is not changing on the level surface. This is 0. So del f is perpendicular to any unit vector tangent to the level surface, or I can say del f lies in the direction normal to the level surface. So I can write, I want to prove, I can prove this. See, del f lies in direction of normal. Right now I won't write this, but I can see over here that del f is perpendicular to n. So if del f is perpendicular to n, so this directional derivative in the direction of normal will be given by this del f dot n. Since del f is parallel to n, so I can write this del f mod of n into cos 0, that is mod of del f. So del f mod of del f is nothing but directional derivative. So I can write, I have two information. One, del f is parallel to n, and one, the modulus of del f is nothing but the magnitude of directional derivative in the direction normal to the level surface. So I can write like this. I can have this del f equals to df by dn. Del f equals to the magnitude of del f is the directional derivative in the direction normal to the level surface, and it lies in the direction of normal to the level surface. So I can write this del f vector as this. So this is second property of your del f. This is a gradient of f, right? So I'll move on to the third property. So this is the third property. Del f, the gradient of f is a vector in the direction of which the maximum value of directional derivative of f occurs. See, del f by del s is nothing but dot a, right? See, this del f lies in direction normal, lies in the normal direction. So I can say, if suppose del f lies in direction normal to the level surface, and a is a unit vector in some direction, so I can say this is nothing, this is a unit vector, so I can write it as del f mod of del f into cos theta, mod of del f into cos theta, where theta is an angle between del f and a. So when do you think, for what value of theta is this directional derivative is maximum? I can say df by ds is maximum if theta is 0. The maximum when theta is 0, or I can say when a lies in the direction of del f, or normal to the level surface. So I can say the directional derivative is maximum in the direction normal to the level surface, and that is the direction of del f. From the previous property we saw del f lies in direction of normal, and we have proved that del f, this directional derivative, is maximum in the direction normal to the level surface when theta is 0. So df is maximum in the direction normal to the level surface. So I can very well say grad f is a vector in the direction in which maximum value of directional derivative of f occurs. So this is the properties. There are three very important properties of the gradient. Now we will see some examples, some application of gradients.